Okay, welcome to this session. So in this session, we will apply Gauss-Seidel method and Newton-Raphson for a power system analysis. So we'll take a three-bus system, simple three-power system as an example. And our case, we have one slack bus, one PV bus, and one PQ bus. So proceeding to the problems, we know that for slack bus, the magnitude of voltage and angle will be specified. There's no need to calculate for these two parameters. Again, when we come to the PV bus, the active power and the voltage for this bus will remain constant as specified for a PV bus. Again, we have a PQ bus where the both active and the reactive power will be specified. This is a load bus. And we will calculate the magnitude of voltage and the voltage angle is bus. So the general specification for our system is given here in the table. We have a slack bus uh, uh, where the voltage is given as 1.04 at 0 degree, and the magnitude of active and reactive power will be varied based on the power mismatch for a slack bus. In addition, we have a PV bus where the voltage, magnitude, and active power is specified, whereas reactive power will be calculated based on the power mismatch. Again, we have a PQ bus, and this we have specified active and the reactive power, but voltage and the voltage angle will be calculated. So in a representation, we have this legend. This means it's a generator. This symbol is for a bus, and this straight line is for a transmission line, and this arrow is used to indicate the load, so you can understand the ways. So we have also a transmission line impedance. Here it is specified in this table. So we'll go to the formation of Y bus, assuming that the internal impedance of generator is 0, or we can ignore it, and we have 0 bus to ground shunt admittance. In addition to that, we have this equation for a power flow calculation. So the power at each bus can be calculated by using this equation. This is a general equation we obtain when we derive for the power at bus I. So proceeding to a Y bus formation, already we have this reactance. So the inverse of reactance will give an admittance and a conductance, but we have only the reactive or uh, imaginary part of impedance. So it's reactance. So by forming a Y bus, we have uh, two main components for a Y bus formation. One is a diagonal component, which is the summation all admittance connected to that bus. For example, here we have 1, 1. So this 1, 1 means is the summation of y10, y12, y13. So for a y1, 2 we have here 0.2. If we take inverse, it becomes 5. 1, 3, something like 0.3. If we take the inverse of it, it becomes 3.33. So the summation will be 8.3. Like that, for all bus, we'll add the bus admittance connector to that bus to obtain the diagonal Y bus component. But for off diagonal component, for example, we have symmetrical here. We can see this also. This is similar. So once we calculate the one symmetrical component, we can use it for example, if we see the Y admittance y12, y12 means is the impedance that connect bus 1 to bus 2. So if we take this as inverse of it, it become 5. In addition, there is minus sign here. So the off diagonal is obtained by taking the inverse of the impedance and taking the inverse of that. So here we have 5, again we have 5. 3, 1 is also from 1 to 3 to 3.3 minus 3.3. So if we take the inverse of that, it becomes 3.3. So 3, 1 is similar. Like that, we perform this Y bus. It's very simple and straightforward. Then we will go to initialization. For a slack bus already given, the voltage is constant for any iteration, and the voltage angle is also constant. For PV bus also the voltage is constant. What will vary is only voltage angle. For a PQ bus, both voltage and voltage angle will be vary based on the iteration and the power mismatch. But we have a PV bus for bus 2, and the magnitude of a bus active voltage will be remain constant. There is no need to calculate at every time, but we can calculate the reactive power here for bus 2. Again, for the bus 3 is a load bus. The active and the reactive power will be specified, but the voltage will be calculated. So proceeding to the Gauss-Seidel scheme, the voltage magnitude relation to the power as well as the voltage at other buses obtained by using this equation. So for a first iteration, we can use this. The magnitude of a slack bus voltage is the same, so no need to calculate the slack bus voltage and angle. So we'll skip slack bus voltage 1 bus calculation. So we can proceed to second bus voltage calculation. So to go to that, we will have PV bus. We have a PV bus in the second bus. Again, the magnitude of the voltage is the same for a PV bus. No need to calculate because it's PV bus. For that, power and voltage will remain the same, but we can calculate a reactive power and the voltage angle at its time. So no need to go for that. But if you go to for the third bus, which is PQ bus, the first iteration can be obtained by using this. So Y33, P3, Q3 is already given. V3 prime is given, already angle is given. So we can take conjugate of that, then minus the summation of Yj, Vj, K plus 1. Already for PV bus and slack bus, the voltage is the same. We can use that for the second iteration. For the first iteration at a bus 3. For a PV bus, we can compute a Q2 from the above equation. Q2 can be obtained already on slide 1. We have equation to compute the active and reactive power at each bus. So we can use that to calculate for the first iteration. When we go for a second iteration, the voltage is the same. So we'll go to second iteration for a bus 3. Again, we can compute the reactive power at bus 2 after we compute a voltage for a third bus. Update V2 magnitude to this because with the same angle, no need to calculate. So we will proceed in this way for a Gauss-Seidel to obtain the solution. For example, initially voltage is given like this. So maybe a third voltage after first iteration is calculated like this because third voltage after first iteration. Then if you go to the second iteration, V2 is 1.09 at angle of V2 is V2 2. V2 2 means the voltage at second iteration, whereas the third voltage is obtained for second iteration like this. So the convergence tables can be obtained like this. So for initial for V2 is changing like that. Angle is here for V3, then uh, uh, surge voltage angle is like this. So V2 voltage angle is varying. We can calculate a voltage angle. Voltage angle we can calculate because already we have V2, which is 1.02. No need to vary the voltage. Already voltage is the same, but we can calculate an angle. By taking the calculation of voltage, we can see the angle update. Like this, Gauss-Seidel converter. So we can proceed this up to n times and obtain the voltage magnitude. So when we come to a Newton-Raphson, the limitation of Gauss-Seidel is that it's work only for a linear system where the relation between input and output is linear. But when you see the power system, especially the relation between a voltage and the power voltage angle and the power is not linear. So for that purpose, Newton-Raphson is more important and more relevant to calculate the magnitude of those parameters as a function of input parameter. So what we'll do is that we first identify the state variable, the variable we are going to calculate after each iteration. Then we will perform a Jacobian matrix. Jacobian matrix is the partial differentiation of a function with respect to a state variable. Then we'll specify the flat start. Then with a flat start, we'll calculate a Jacobian matrix, and we define our correction variable magnitude. Then we'll calculate again the function value at a flat start, and we'll solve the equation. That's the Jacobian matrix multiplied by correction factor is equal to minus the value of function at flat start. So we can do like that. So for example, if we take alpha 2 is a voltage angle at bus 2, alpha 3 voltage angle at bus 3, and voltage magnitude 3 as a state variable. This is state variable. Then we can assume the initial magnitude for voltage angle at bus 2 0, voltage angle at bus 3 0, and magnitude of voltage at bus 3 1. So at k is equal to 1, we'll calculate the magnitude of flat start. So by calculating a voltage, changing the variable like this, we'll solve this magnitude. What we call Jacobian time correction factor is equal the negative of the function evaluated at flat start. So by solving that, we calculate the change in variable. So change in variable plus original variable will give the updated new one. So like that, we'll calculate and perform the iteration, and finally we'll stop when there is magnitude of error is less than the tolerance value. So like that, here mismatch at k is equal to 0. Mismatch at k is equal to 0. For example, at change in P2 is equal to this, the function value at 0 at the initial start, then change in P3, change in Q3. This P2 is the power at the flat start. This change in P2 at bus 3, change in Q3 at bus 3. So solve this equation. By solving this equation, we can obtain the magnitude of a voltage angle after each specified time, and now we'll correct this. The correction is like change into this, change in this, and this. Like. So updated one is we'll add this to the initial value, and finally we'll solve. If the magnitude of the voltage difference or angle difference is greater than the tolerance value. So we'll calculate the new update. So like that, we will go for that. So initially we have this voltage magnitude, then this voltage magnitude and the current. Now we update it by solving the Jacobian matrix. Jacobian matrix times correction factor minus f of x equal to 0. So first we'll check the convergence. For example, if our initial guess is working and the difference is less than the magnitude of tolerable error, we can stop there. We can assume the initial guess is that. So this is the maximum mismatch. For example, we have this max mismatch, or here we have voltage mismatch, power, and change in curve mismatch. So this minus not actually like this, the minus function. So we can proceed in that way and solve the Newton-Raphson equation.